Okay, so this is the first problem of this tutorial. So we'll be solving this question. So you can see here. Let's read this question. This is a quarter cylinder. Radius is 1 meter. It is hinged at a pivot point A on top of a wall, which separates two fluids. We have fluid 1 and this is fluid 2. So you can say fluid 1 and 2. This fluid density is given 1000. The second fluid density is given 1400. So gate is 4 meter long. The gate we have, it is 4 meter long. So we can write the length equal 4 meter. You can say length L equal 4 meter. And it is direction onto the base. So you know this. And it is in the static equilibrium condition. For the first question, for the first fluid, we need to determine the resultant force and position by fluid 1 on the gate. So what is the resultant force and what is the position of the force actually acting on the gate? So we'll solve this question. So you can see this schematic and you can see the solution from our canvas side. Let's say this is the centroid. We just took this point. Let's say this is centroid, this is CP, center of pressure, and this is point A, this is B, this is point D. We have free surface, atmospheric pressure. So you can assume that this is the gas pressure, 0 gas. The length of the gate is 4 meter. Horizontal force always acts like this, and all of you know it acts to the center of pressure. So it's the horizontal force acting this way, the vertical force acting this way. Let's say this is the the point where the vertical force are acting. This is the resultant force. Let's say this is acting this way. We know here. So what we will do, this is a curved surface. So we will actually, calculate the horizontal force and the vertical force, and then we will calculate the resultant force for this problem. So this is the horizontal force, this is the vertical force. It is the center where the centroid, where the average pressure works, where the the center of pressure, the result, we can say the center of pressure is the point where the resultant force acts, that we know from the previous theories. Here what you can see, this height C, this is the height of the centroid. This point, we said this is height C. Radius equal given R. The C and the CP distance, let's say this C and CP is delta CP. Okay, delta CP, that's the distance. This distance, let's say this is the wall and this is the vertical force acting. Let's say this distance is x1. We have two theories here. Basically, for a submerged problem, the delta CP is the distance from the centroid and the central pressure. So this distance can be calculated based on this formula. So it is the IC, second moment of inertia, length, area, and especially for a semi-cylindric, semicircular thing, the distance is 4r over 3 pi. So it is basically this one, x1. So 4r over 3 pi. So that we know from the theory. So nothing new actually. And this delta CP, we have another formula. So then we'll be using that formula when we'll calculate that distance. The first thing is the horizontal force. So if I write like this, the horizontal force. Horizontal force, we can say the phase 1 or a phase 1, the way it is solved in the problem. So it is the pressure and the area, or so pressure where on this surface AB. This is the vertical projections. The horizontal force acting on the vertical projection AB. So pressure on AB, we know it is rho G. rho 1, say rho 1, this is the fluid one, and the haze is the height of the centroid. So we know, because this is the average pressure at this position, average pressure works. And the area A, this is the area for this section AB. So this is actually what we know. Now density is 1000. Let's say this is kg meter cube. Gravity is 9.8 on meter second square. The height is C. This radius is given 1 meter. Okay, so we can say AB equal 1. AB equal 1. So what should be the centroid locations of the haze C? It is just AB over 2. That means it should be like 0.5. So the haze C is 0.5. Now the area. So the area is, it is two-dimensional thing. Maybe we know the height and the length. So in this problem for AB, we know the AB length is 1. That we can say radius, and the length of this gate is 4 meter. So we just multiply, say meter square. If we simplify this, then F has 1. It will be 19,620 Newton. So this is, we got the horizontal force. Okay, the horizontal force. And now we can calculate the location, like where exactly the horizontal force is acting. So we know it should be this position. So that means it is, we can say this height and this delta Cp. So the location, we can say the location of F has 1. So this is what we can say is delta Cp plus haze C. This haze C is the the height of the centroid, and delta Cp, we said this distance. From the next slide, we said delta Cp is Ic and Lca. So substitute this value, or we can just calculate it like this. Delta Cp, this is Ic. This Ic is the second moment of inertia, and this is the A, or the area of AB. Okay, in the solution, it is written like AB. That is the area. Okay, I see. This is basically the second moment of inertia. It is, if we assume it like this is the length of the gate 4, and if it is the radius 1, so we can say this is kind of a rectangle. So we can use the formula for the rectangle. In the chart I showed you during the lecture, it is AB cube, over 12. This is the IC, and LC here, or so this is basically the length or the height of the centroid. You can say the LC, you can say LC, hey, see, this is same. So it is 0.5. Okay, so 0.5. And the area of AB is 4 into 1 meter squared. So here, so basically, if when we discussed it later on, so the here, if you see, it is actually ABQ over 12. This for this rectangle here, we know the formula from previous from the lecture slide. So what I'm going to do, I'm just going to, this is 1 meter and the force was acting this way. So this is basically, we can say this is 1 meter. So if you see the force is acting this way, so it will be always the cube term. It's the A B cube over 12. So this one, it will be the cube term, especially when it's the second moment of inertia. You know this. So I'm just writing it here. The for A equal it is 4, B equal 1 over 12 by 0.5 into 4 into 1 meter square. So this delta Cp, it will be 0.1661, 0.1667. So this is the delta Cp. We need the location, and we say this location is delta Cp plus the the centroid distance. So we'll write it in the next page. So the location, it will be delta Cp plus the distance of the centroid, the height of the centroid. So it is 0.1667 and it is 0.5. So it will 0.667 meters. So this is the answer, basically, like where it is acting. So this distance, I mean from here to here, this is the distance actually that it is working. So we have done for the horizontal force. Now we need to calculate for the vertical force. For the vertical force, we will move to the next page here. So if I draw a line, vertical force, we know from the formula Fv. So this is equal, you can say the weight acting on this. So, or in other words, we can say the density, you can say gravity, and the volume. So volume is basically on this quarter cylinder ABD, that is written in the solution, or we can say rho on G and the volume of ABD. Now the volume means this three-dimensional thing, the quarter cylinder, or you can write it as rho on G into the volume means area, length. Okay, it is a the volume of ABD, it is just a quarter of the area. You can divide by 4 because you need the volume for the quarter cylinder. So you can say it is rho on G. Area is pi r square over 4 into L. You can write it like this. Or here r is the radius, so radius is 1. Radius is 1. So you can substitute these values here. Density 1000, so gravity 9.81. Radius is 1, length is 4 over 4. Okay, so this will be Fv, it will be 30,819 Newton. So this is the vertical force. We have got these two values. So now if we want to calculate the resultant force Fr, so this is F Hayes square and Fv square. I think we previously said F Hayes 1, so you can say it is F Hayes on Fv1. Yeah, whatever notation you use, it doesn't matter. So the horizontal force was, if we go back, it's 19,620. So 19,620 square, and it is 30,819 square. So this value will be, the final value will be 36,503.93 Newton. So you can calculate it, this value, and see whatever you got. So I believe this is the answer, 36,530 something. So this will be the the resultant force. Now we need the distance. So this is the vertical force acting. You see, this is the vertical force acting. So what is the distance between this wall and this vertical force? I mean the center, x1. And we know from the previous formula, it was this distance. I just showed you this formula previously. So this, we said this is x1. So I showed you all the calculation. It is 4r over 3 pi, and r is actually 1 here. So it is 4, r is the radius, and 3 pi. So this x1, it will be 0.4244 meter. So this is what we have got, the x1. So we know the distance, right? So we have now the distance, and we have now the resultant force. So that's for the first part of this problem. If you can remember, the first question says we need to calculate the resultant force, Fr. So we calculated F-1, F1, this is the resultant force, and this is the distance for the vertical force, and for the horizontal force, we calculated the distance, this distance earlier, and it was, yeah, it was the formula. So yeah, it is 0.661. Second problem is, if you know the density for this fluid is 1400, determine the resultant force and the position by fluid 2. This is interesting problem. So we need to determine the resultant force for the second problem. Here, when it is actually, acting this way, we need to calculate the, so this is the planes here, this is the wall, this is the curved surface, the F-1. So we will have a resultant force F-2 this way, F2, which will act on this plane surface. So that's some kind of the reaction force that will act in this surface. But we have no water block in this position, so we'll have no vertical force, but we'll have the horizontal force. We know from the Newton's second law. So we will have some resultant force, I mean the reaction force here. So we can say this is B. So the resultant force due to the fluid 2, this fluid 2 will apply some force on this plane surface, right? So we can say it is F is 2. So this is equal, again we can say pressure and the area. So the pressure is rho G H. So rho is rho2, density of the second fluid, and this is the centroid height, and the area is area of AB. Second fluid density is 1400, gravity 9.81, and the 0.5 meter is the centroid locations, and the area is, we already know, 4 into 1. So this will be 27,468 Newton. This is F-2 that we got. That's the resultant force here, because we have, basically just the one force acting on the surface. Now we need the distance. So the distance is again the same. This distance, we will say this is delta Cp, and this plus this distance, right? So let's calculate the delta Cp first. Delta Cp, this is equal, the formula we know, Ic, and Lc, what the HC, this is the same, into the area of AB. Right, so it's the same problem that we know. Ic, we previously calculated like the AB cube over 12. So AB cube over 12. So write it, AB cube over 12. HC, this is equal 0.5, and the area is 4 into 1. So it is the 4 into 1 to the 4 cube over 12 over 0.5 and 4 into 1. So delta Cp, it will be the value, the same value here. We will get 0.1667 So because they are both acting in the same position, so the distance is, it will be the same answer, delta Cp plus C. So it's 0.1667, 0.5, so it should be 0.6667 meter. So this is the solution. So what you have done here for the second problem, we don't need the resultant force. I mean, we don't need the vertical and the horizontal things, but we need only the horizontal force, which is actually acting due to the fluid too. So I hope you understand this, and this is the solution for the first problem of this tutorial.